Good day, everybody. Welcome. My name is Andrew Johnston. I'm the Vice President for Astronomy and Collections here at the Adler Planetarium in Chicago. Really glad you could join us today for our 7th Kavli Fulldome lecture. We have a really special experience for you this day. For those of you that have not been to one of these lectures before, we do something a little bit different than your average planetarium show. You're going to be seeing our two speakers talk about how we understand and explore the universe, and they're going to be doing it with visuals that fill the dome over your head. These visuals were produced by our team here at the Adler, and they'll actually be run in real time. There's somebody at the back of the room actually flying them while we're sitting here listening and learning. In addition, it's not just happening in Chicago. Right now, as I'm speaking, there are multiple venues all over the world that are tuning in. They're hearing us and seeing the same visuals that we are here in Chicago. And the map, is the globe still behind me? Yes, it is. If you look at the globe behind me there are actually some marks that indicate some of the partner sites that we've got all over the world. We did this program last night, and we're doing it today to hit different time zones. And I'll share with you some of the specifics of those partners after our talk. But today, it's my pleasure to welcome our speakers. Joining us today are Chris Lintott and Laura Trouille. Chris Lintott, who's over there, is from the University of Oxford, where he's a professor of astrophysics. He also leads many efforts to connect the wide public with science. He hosts a TV show on BBC, The Sky at Night. He's also just written a book about citizen science, The Crowd and the Cosmos, Adventures in the Zooniverse. Joining him today is Laura Trouille, who is our Vice President for Citizen Science here at the Adler Planetarium, and I'm proud to say she's my colleague on part of the leadership team here at the Adler, where besides leading the citizen science efforts that you're going to be learning about here, she also leads programs that engage students of young ages in the doing of science. Together, our two speakers today lead the Zooniverse. Zooniverse.org is the world's largest online citizen platform, where there are millions of people all over the world engaging with dozens and dozens of different science research projects, many of them astronomy related and some not. It's a really exciting way of doing science. And what they're going to be doing today is talk a little bit about how that works, how we know what we know about the universe, and how doing science in this way leads to some exciting discoveries, and how scientists work with people all over the world in expanding the frontiers of knowledge. So without further ado, please join me in welcoming Chris Lintott and Laura Trouille.
Thank you very much. Thank you all for coming on what is another beautiful, warm Chicago day in November. It's lovely to see you all here. I'm very excited to go on this journey with you this lunchtime. I'm particularly excited to be here in particular because we're inside the dome of a planetarium. And planetaria are my favorite places, partly because we could show you the night sky in all its glory, but also because with the powerful technology and the skills of the team here at Adler, we can do things like this. Transport you for no extra charge into deep space and travel through the large-scale structure of the universe. What you're looking at here is a survey of 1 million galaxies. So each of these blobs that you see around you is a system of perhaps 100 billion stars, each the equal of the Milky Way, our own home in the cosmos. And these are 1 million out of the 100 billion or so galaxies that fill the observable universe. This visualization gives us the chance to explore our cosmic neighborhood, but I also think is visually stunning. And I honestly think we could have a happy 45 minutes just drifting through the cosmos without us saying anything at all. It really blows my mind.
I'm also drawn into this enormous data set because of the tremendous potential it represents in terms of furthering our understanding of the universe. One of the main reasons I was attracted to the field of astronomy is because there are so many open questions, so many mysteries, so much that's still unknown. When I look at this data set, I think about all the answers hidden inside, waiting for us to discover them, and all the new questions those discoveries will uncover.
Amongst the grandeur and the beauty of the universe, there are individual, remarkable objects that hold the key to understanding our cosmos. In this talk, we'll take you to a specially selected handful of them, each of them discovered not by professional astronomers, but by volunteers, members of the public, participants in the Zooniverse. And I hope to convince you that you too can help us explore these grandest of scales. But let's start here, in the realm of the galaxies.
100 years ago, two astronomers, Shapley and Curtis, debated if ours was the only galaxy or if there are others in our universe. Just 100 years later, we have this amazing data set of 1 million galaxies from the Sloan Digital Sky Survey. Back in 2007, a small group of astronomers, including Chris, were poised to pursue research with these data. But before diving into their research questions of interest, they first needed to know, for each of these galaxies, was it a spiral-type galaxy or an elliptical-type galaxy? Spirals, like our own Milky Way, have structured arms and ongoing star formation. Elliptical galaxies, on the other hand, are soccer ball-shaped.
Football shaped.
Potato.
It's an international audience. We need to translate these things.
Often with lower star formation rates. So the team set to work classifying galaxies. Kevin Schwinsky, for example, managed to classify 50,000 galaxies in 1 month. That's an impressive feat, but just a drop in the bucket of the 1 million galaxy dataset. On their own, it would have taken this small team of researchers more than their professional lifetimes to just classify the galaxies, let alone actually dive into the research of interest. At the time, Angry Birds was quite popular, with the public collectively spending 5 million hours every day playing. So the team wondered, could they harness the power of the crowd for research? So Chris and his team launched the website Galaxy Zoo in 2007. In the first hours, they were getting 70,000 classifications an hour. In the first year, over 100,000 people participated from around the world, providing millions of classifications.
It's an impressive number of people. It's an impressive amount of effort provided by our volunteers. But the really impressive thing is that collectively, the classifications provided by Galaxy Zoo volunteers outperformed not only the computer systems we had at the time, but actually the public were better than an expert at doing this, taken collectively. We have about 40 people look at each galaxy, and you can see the results on the dome above us. Where people have voted for spiral galaxies, we've coloured the donut surrounding the galaxy blue. Where people have voted elliptical, it's red. And you see in most galaxies there's a clear consensus. We're good at labelling these galaxies. You'll see a few where there's more disagreement. Some people think it's an elliptical, some people think it's a spiral, and that's okay. With this sort of method, unlike if we have a single expert or single tired student classifying all the galaxies, we get a classification, but we also get a confidence. I can tell the difference between a galaxy where 40 out of 40 people say it's a spiral from one where perhaps only 30 people say. And that turns out to be incredibly helpful and useful. We found in the original Galaxy Zoo that we agreed with Kevin's classifications 98% of the time, and in the other 2%, the crowd were more likely to be right than he was. A single expert inevitably makes mistakes, but our crowd of volunteers on the internet do not.
Over time, Galaxy Zoo data have been used in over 300 publications and have had a major impact on our understanding of galaxy morphology and evolution. For example, through the dome, we can show how we've learned that spirals tend to live along the filaments of the cosmic web, in the suburbs, if you want to say. So here we're just showing the known spiral galaxies. And the ellipticals tend to live in the denser nodes. And so we can switch from looking just at the spirals to looking at the ellipticals. And this is where, in those nodes, it's more like the downtown of a busy city. There's a lot of activity and interaction going on. So ellipticals are often the result of cosmic collisions of spiral galaxies. The differences are relatively subtle. Another reason why you need all the galaxies to be classified.
I think you can see that it's a subtle difference just from seeing it on the dome. It's a fascinating example of using the planetarium software to do data visualization. I knew this result, but until I came here, I hadn't seen the difference between where the ellipticals live and where the spirals lived. In Galaxy Zoo, we went on to do a lot of work about the populations of galaxies that we saw, the sort of census that we could derive of this large population. But what we want to talk about today are the unusual objects, the surprises amongst the multitude of galaxies. Sometimes a single system can tell an important story if you can find it amongst this vast panoply of data that we find ourselves in. The person who taught us this was a Dutch school teacher called Hanny van Arkel, who was the first to see the galaxy that's up on the dome behind me. If I showed this image to a computer that was well trained to classify galaxies, it might tell us that the central system is a sort of dusty spiral. But you're people, you're distractible in a good way, and you're wondering why there's a blue blob, a smudge on the lens hanging beneath the galaxy. And that was the question that Hanny asked as well. Now, I said Hanny was Dutch. She called this a voorwerp, which we thought was a technical term. And so in the scientific literature, this object is now known as Hanny's voorwerp. Turns out, voorwerp means thingy in Dutch, or object. But still, it's a good name, I think. Hanny presented us with a puzzle. She asked the most basic and profound of scientific questions. She asked, what is this? What is this weird thing that I wasn't expecting? And so we tried to find out. We got a friend who had time on a telescope in the Canary Islands to sort of unofficially point his telescope in this direction and take some data. And the data told us a few surprising things. First of all, it told us that the voorwerp, this blob, is at the same distance from us, roughly, as the galaxy. And so that means it's big. This is a galaxy-sized blob. I do use these technical terms like blob, but this is how we talked about it ourselves. Secondly, we found out that the voorwerp is made of hot gas. That's why it's glowing. In fact, it's made of gas that's about 50,000 degrees, 50,000 Kelvin, 50,000 centigrade. And yet, there are no stars within the voorwerp. And so we have a cosmic mystery. How do you heat a galaxy-sized blob of gas to 50,000 degrees if there are no stars there to energize it?
So to try to find answers to all these questions and deepen our understanding of the galaxy, particularly the galaxies that's above the voorwerp, we went on to take images with Hubble Space Telescope and other telescopes. So first, just a note that the voorwerp here shows up green in the Hubble image and blue in the Sloan image, just purely for aesthetic reasons. It's the same energy bands and emission lines in both.
It also looks more like an angry Kermit the Frog in the Hubble image, which I think is an improvement.
And so this new data pointed to the presence of a supermassive black hole at the center of the galaxy. Most galaxies, including our own Milky Way, have an intermediate mass or supermassive black hole at their center. The discovery of the voorwerp has taught us a tremendous amount about what's going on, what the interaction is between that central black hole in the galaxy and its surroundings. It's a topic dear to my heart. My PhD thesis and postdoc research was on active galactic nuclei, or galaxies with active central black holes. This particular galaxy is 650 million light years away from us. At its center is a black hole thought to weigh millions of times the mass of our sun. Typically around an active black hole, there's an accretion disk of material flowing inwards. This accretion disk, in turn, causes a powerful outflow of high-energy particles beaming out into the surrounding intergalactic medium. When that beam hits leftover tidal streams of a smaller nearby galaxy, it causes that gas to glow, energizing emission lines of glowing oxygen in particular. So that might explain the presence of the voorwerp.
It's an excellent theory, but in science and in observational astronomy, we try to test our theories. And so when we had this idea, we thought we could easily test it. If there is an accretion disk around the black hole at the center of the galaxy next to the voorwerp, then it will be made of hot dust and gas. And that gas will shine brightly in the X-ray region of the spectrum, be hot enough that it will emit X-rays which will penetrate the dusty heart of this galaxy. And so what we did was we used a space telescope called XMM Newton to stare at this galaxy and look for the signs that there was a hot accretion disk around the galaxy. We stared and we stared and we stared, and we found absolutely nothing. There's no hot gas at the center of that galaxy. And so what we think has happened is that we've caught the galaxy in a state of transition. 50,000 years ago, the black hole at its center would have been feeding vigorously. It would have had this hot accretion disk that Laura described. But because it's run out of material, or because of some process that we don't yet understand, it's now switched off, leaving the galaxy quiet and the voorwerp the only witness to what happened just a few tens of thousands of years ago.
And since finding this first Vorup, we've found only about 20 others to date. The rarity of finding such an object is an additional indicator that black holes turn on and off in a cycle of eating material and then pushing that material away, and that these cycles happen on relatively short cosmic timescales. For this galaxy, we think that the black hole switched off, as Chris said, about 50,000 years ago, but because the green blob is only a few tens of thousands of light years away from the galaxy, it's provided us a ghost remnant of that black hole's activity. So not only can you participate in Galaxy Zoo online, but over the past 18 months, we've built a completely unique Galaxy Zoo touch table experience, especially designed for museum guests. So here at the Adler, and hopefully soon at other museums, you can choose which galaxies you want to classify, talk with your family and friends about your choices, send them a galaxy you're unsure about, and look into and understand how the researchers are using these data for this research. Since the launch of the table experience just this August, Adler guests have classified over 80,000 galaxies and counting. We can't wait for other museums and science centers to take advantage of this new way to engage their guests in real research during their visit.
This is the only Kavli lecture to have an infomercial in the middle, so I'm talking to those of you who are at our remote sites. If you'd like to classify galaxies in your museum, it comes with a guarantee that your classifications will actually be useful. We've tested this, and Adler visitors at least are as good as people on our website classifying galaxies. Then do mention this to the museum staff as you leave the lecture today. Here ends the infomercial. What I want to do now is head back towards the Milky Way, because what happened when we launched Galaxy Zoo was not just that we were surprised by the willingness of a large crowd of people to help us out. Not only were we surprised by things like the Vorup and Honey's ability to be distracted, but other scientists, from penguinologists to cell biologists, started contacting us, wondering if the people who helped us might help them with their data. This problem of having too much data to sort through, of having got too good at collecting information about the world we live in and not good enough at analysing it, turns out to be common across many fields. And so Zooniverse was born in 2009, supporting projects from astronomy to zoology, from classifying galaxies to identifying animals in images from the Serengeti, to marking cell structures for cancer research, to in a project that just launched a couple of weeks ago, transcribing the registration cards of African American soldiers who participated in the Civil War. There are now nearly 2 million registered participants in the Zooniverse, including 20,000 Chicagoans taking part in more than 100 active projects. But my heart, though it's been fun to be distracted by penguins and everything else, my heart has remained in astronomy. And we've increasingly realized that Zooniverse and the work of our 2 million volunteers can help us address one of the big problems of modern astronomy: how to deal with the transient universe. We've already talked about the fact that the Vorup changes, or tells us that the galaxy has changed. But when you look at the night sky, it's not as static as it seems. Stars pulsate, they interact. Galaxies change as their black holes vary. And even in our solar system, we're seeing all sorts of phenomena that change over time. And we need help to look at this transient universe, which is everywhere that we look.
And here we're showing a model of two stars orbiting each other. As one passes in front of the other, imagine how the light gets blocked, and a telescope here on Earth would momentarily receive less light. Astronomers use this transit method, as it's called, to look for planets orbiting distant stars. If the star's light dips in a regular, periodic way, that can be an indicator of the presence of a planet passing in front of and behind the star.
This sort of technique has been used to look for planets, as Laura says, and it's been instrumental in, I think, the great scientific revolution of our time. When we look at the night sky, like the one simulated above you now, or when you go outside this evening, look up and see the stars in the night sky, you should know that we now think that most of those stars have planets. When you look at the night sky, you're seeing a scattering of potential systems with worlds in orbit around them. And I think there's a philosophical and scientific shift that we're going to have to make to come to terms with that. The telescope the instrument most responsible for that is a NASA satellite called Kepler, which for 3.5 years did the most boring job imaginable in the universe. It stared at the same patch of sky, and for every 29 minutes, it told us the brightness of 150,000 stars, looking for the dips that would indicate the presence of planets. One such star, studied by Kepler, is this one. This is a star known as K2138. Terrible name, don't let astronomers name anything. But K2138, we now know, has planets around it, and they were discovered not by professional astronomers, not by algorithms sorting through a computer database, but by volunteers on our website Planet Hunters looking for the dips that indicate the presence of the planets. This one in particular was found by Andrew Gray and friends. Andrew's a car mechanic in Darwin in northern Australia. He found a system of 5 planets, and there's a pattern here. If you take the innermost planet, for every 3 times that goes round its star, the next one out, planet number 2 if you like, goes round precisely twice. And so they line up every so often. In fact, every 3 and 2 orbits. If we go around one more, you'll see there's an alignment there. Now that second planet, for every 3 times that goes round, the third planet goes round twice. So they line up too. For every 3 times the third planet goes round, the fourth planet goes round twice. For every 3 times the fourth planet goes round, the fifth planet goes round twice. This is called a harmonic series, and this is the largest chain of such planets we know. I think we've just sped up time slightly. So does the pattern continue? Are there more planets? One could imagine, and because we're in the planetarium we can see, adding more planets. Let's add a 6th planet to the system. No expense spared. Here we go. We'll make it blue so that you remember that it's not there. And actually, so this one's set so that for every 3 times the outermost planet goes around. Oh, there we go. That's the one. Thank you, Mark. Let's add a 7th planet to the system. And you could imagine repeating this pattern. So let's add an 8th planet, and each of these is at the 3-to-2 resonance. Now this one in red, it turns out we know that one exists. So we've detected hints of a 6th planet that we were able to follow up with NASA's Spitzer Space Telescope and discover that there was indeed a 6th planet in the system. But there's something odd going on here. That 6th planet almost but doesn't quite follow the pattern of the other planets. The fact that there's this resonance for the planets shown in yellow tells us that they formed together in a sort of stable, unchaotic process, and that they've been stable ever since. The red planet nearly but doesn't quite follow the pattern, which is telling us something interesting about planet formation. But what are these blue ones that we haven't found? Well, what we're showing now is why we might not have seen them. You can find an angle such that the red planet and the yellow planets transit in front of their star. From our perspective, the planets cause blinks because they cross in front of the star itself, whereas the blue ones may be on inclined orbits so that they never pass in front of the star. So what we have to do is work out how we might test whether these blue planets exist. We can't use the transit method. Well, luckily, there's a solution at hand. Each of the planets will pull on its neighbors through its gravitational attraction. That will cause some of the planets to arrive early or late for an expected transit, maybe as much as 8 minutes early or late. And a European Space Agency satellite called Cheops is being launched in the next few weeks, which will have this system as one of its main targets, looking for those tiny variations in timing that will suggest whether there are extra planets in the system not yet discovered. So we've gone from somebody in Australia looking at a computer screen, wondering if they could see evidence for a planet, to an international space agency launching a mission which will target a system that a couple of years ago no one knew was interesting. I think it's a remarkable testament to the power of citizen science.
And K2138 is a great example of a Zooniverse discovery by our volunteers as a result of classifying hundreds of thousands of light curves. The next example we're going to share is of a discovery driven by our human ability to recognize the unusual and unexpected, to flag it and wonder and ask the question, hey, that's weird, what do you think? So just as Hanny found one galaxy amongst the millions, so sometimes there's a single star worth paying attention to.
The star in question was known as KIC 8462852. Very catchy, don't let astronomers name things. And it was a perfectly normal, slightly sun-like star until it was viewed by volunteers on the Planet Hunters project, particularly one called Darrell LaCourse, who made this a special project of his. Just after Kepler started observing this star, there was a blink, which possibly might indicate the presence of a planet. A few weeks later, that blink repeated. Brilliant, we thought we might have a planet on a few-week orbit. But there was no third blink. And so this isn't a planet. Planets don't go round once and then twice and then disappear. That's not how they behave. They're reliable beasts. And so something else was going on. But the star then did nothing interesting for about a year. And then remarkably, it did something that none of the 149,999 other stars studied by Kepler had ever been seen to do. It dimmed dramatically, losing about 15% of its brightness for about 3 to 4 hours. And then it came right back up to the previous brightness, and it carried on as if nothing had happened. Stars don't do this. This is a complete mystery, and our volunteers started to pay attention. They kept an eye on it, and just before the end of the Kepler mission, a year later, there was a period of a month and a half in which this star misbehaved really badly. It faded, it brightened, it faded, it brightened, it dipped way down and came all the way back up, and then for fun went through a series of shallow dips. We couldn't explain what was going on, and in fact, if I'm honest, we didn't believe what we were seeing. We assumed it must be some sort of systematic effect. We checked the neighboring stars to see if they were showing weird effects. They were all fine. In fact, in one point, in an incredibly tedious task driven by desperation, we looked at which pixel of the camera each measurement of this star was being made with, just to see if there was some systematic effect that we were neglecting. But we couldn't find anything that told us that this wasn't real. We needed a better astronomical explanation.
And alongside the researchers, the volunteers' curiosity was also piqued, including Daryl's, the volunteer that Chris mentioned earlier. They all started sharing ideas within the Planet Hunters discussion forum. So the Planet Hunters project, just like every Zooniverse project, has a dedicated forum where the researchers and volunteers chat with each other about the science and their interests. We strive to create a space where people feel comfortable asking questions, sharing ideas. And so here we're showing the sketch that Daryl created with Microsoft Paint and shared in the forum. Just wanted to share his ideas on what this strange object might be. And he thought maybe it was a dusty ring orbiting around the star. And alongside his drawing, he posted what is one of my most favorite lines from a Zooniverse project. "This is a good opportunity to rampantly speculate." Ultimately, his speculation may not be far from the truth, but just as important was that he felt comfortable flagging the object, sharing his ideas, and engaging with the community of volunteers and researchers to figure this out together.
I think rampantly speculating is an excellent description of what scientists should be doing. And so to celebrate Daryl's idea, we thought we'd produce a slightly better visualization than he could manage in Paint. This is a debris disk around the star. Now, we see disks of dust like this around young stars. When astronomers say dust, think particles a bit smaller than a sand grain left over from planet or star formation. But this is an old star. Just in the last few weeks, astronomers have found a debris disk like this around one such old star, believed to have been caused by two planets colliding within the last few centuries. But you can see why a dusty disk like this might explain what we've seen. You could block the star's light with it, and from here within the disk, we can see in the visualization that it's clumpy. Some of the dust has stuck together to form larger and larger objects. And so if you arrange the clumps in the disk in just the right order, then you can explain the observation that we see. It's a nice idea. Just like with the Volvert, we have a hypothesis. We can test it. Dusty disks like this should shine brightly, it turns out, in the infrared. They're heated by the star, and then they glow in the infrared region of the spectrum. And so we pointed an infrared telescope at this star, but we found no extra infrared signal. The star isn't surrounded by a dust disk. It just sits there on its own. Now, at this point, we tried to write a paper that described to our colleagues what we were seeing, what Daryl and co. had found. And for reasons that surpass understanding, it's kind of frowned upon to write a scientific paper that says, we found a weird thing, we don't know what it is. I think we should be able to write those papers, but we don't. So we came up with an idea that maybe there was a string of exocomets around the star. So comets are nice. They don't emit much in the infrared, and they're sort of icy, dirty snowballs that when they go around their star too often break up. And so we thought if we had a large comet, and it broke up into a string of cometlets, which is the wonderful word which describes pieces of comet, and you arrange them in just the right order along their orbit, then they could cause the blinks. You'd have a small bit that caused the first blink, another bit that caused the second blink, then nothing, then a big bit, and then you'd have a whole host of cometlets which would cause the crazy behavior towards the end of the mission. It's a reasonable enough hypothesis. Unfortunately, people who know about comets read our paper, and they pointed out we needed to invent the largest comet ever discovered by a factor of 1,000, and then we needed it to break up just before humanity happened to look at this completely random star. Just seems like too much of a coincidence. And so we were stumped, and other astronomers started to weigh in. Jason Wright is an astronomer at Penn State, and he and some friends wrote a paper with a spectacular idea for what could be causing the behavior of this star. We visualized it for you here. What Jason and co proposed was an alien megastructure. And the first I knew about this was when I got a phone call from a journalist saying, "I hear you've discovered aliens." Now, I want to pay tribute at this point to the planetarium team here. We asked for a visualization of an alien megastructure. They put an enormous amount of thought into what this civilization would be like. The idea is that this is a power-hungry civilization, and so they've built an immense shell of solar panels surrounding their star. Why just use solar power on Earth or on your planet when you can capture all of the star's light? So this is an old idea. It tends to be called a Dyson sphere or a Dyson swarm. The spaceships you see coming past you now, those are the habitats on which our aliens live. And somewhere flitting about, we've even invented small craft which assemble the megastructure in front of your eyes. They have particularly good systems, I'm told, for getting rid of heat while they're exposed to the fierce glare of the sun. Now, this is, despite appearances, a perfectly sensible scientific idea. Jason and co. said that there were good reasons to believe that advanced civilizations would behave like this, and so it doesn't seem that ridiculous to say that we may have found something blocking its star's light. Here it is. This caused an enormous amount of fuss. I particularly enjoyed the newspaper that accused us of covering up evidence for aliens when we published the paper. And astronomers got interested. A team at Harvard went back through the archives and found historical observations of this star that showed that actually there was another mystery. It was fading gently over the course of a century. So now we've got two mysteries. Why are there sudden dips, and why is this a long, slow fade? Obviously, if you believe the megastructure theory, it's obvious. The aliens are just constructing more and more of their megastructure. And so that explains the slow fading. Thing is, we needed to test this idea. It's a scientific idea like any other. We have a hypothesis. We should test it. And the interest in the star meant that we kept monitoring it even after the end of the Kepler mission with telescopes around the world. A couple of summers ago, the star dipped again, and this time we were ready. We ran out, I think almost every telescope on Earth pointed at the star and took observations while it was dipping. And we showed, while we're still analysing the results in depth, that there's an important result. If you take a red camera that's sensitive to red light and a camera that's sensitive to blue light, the star fades more in the red than in the blue. And so what that means is that whatever's blocking the light can't be a solid object. It's something more likely to be something like a cloud of dust. So no solid object, that means no megastructure, sadly.
And when I was a grad student, I'm sure I never imagined I'd be part of an alien megastructure talk, let alone one that was with the headline, "Zooniverse discovers aliens."
This is serious science, I promise.
And I definitely never thought I'd spend so many hours working with someone who would geek out so much about it. So I'll be the serious one in this duo and bring things back down to earth, literally. So this whole talk is about the unusual and the unexpected. And we don't have to search very far for examples. Even in our own backyard, in our own familiar night sky, we can be struck with surprises. Here we're showing, in a moment, we'll show the Big Dipper. And just above the Big Dipper, this easy-to-spot constellation in our night sky, marked by a circle, is the location of a relatively nearby galaxy, M82.
Because it's nearby and because it's photogenic, M82 is beloved of backyard astronomers and astrophotographers. It's one of the first galaxies I remember seeing through a telescope, hanging as a faint, fuzzy blob in the eyepiece. It was observed by a group of students at the University of London Observatory one night in 2014. They weren't supposed to be looking at M82. They were supposed to be looking at almost anything else, but the skies were cloudy, and so they thought they'd take an image of a familiar object. You can see the images they obtained here. You see, M82 is known as the cigar galaxy because of its long, extended appearance. Those students, despite the fact they were at the University of London, which has the world's worst site for an observatory, it's next to one of the main roads that leaves London. In fact, if you stood outside at night here, you would see more stars than you do at University of London Observatory. They made a remarkable discovery. The images they took that night, which hopefully we can flash up on the screen, there you go, show there is an extra star in the galaxy. And we've added the little check mark so you can see it. This is a supernova, an exploding star, which had been seen first not by professional astronomers with automated techniques, but by a group of students and their supervisor, Steve Fossey, who knew the galaxy well enough to instantly recognize that there was something new. They managed to get a second image to confirm it was real. They announced it to the world, and it turned out to be a particular kind of supernova, which we call a Type 1a supernova.
And we can fade from this image to a higher resolution Hubble Space Telescope image of the galaxy and see a little bit more of the structure of the galaxy itself. This particular galaxy has incredibly high star formation rates, and because of this, there are tremendous stellar winds pushing material outwards. That's the red shimmery material that you see in the image. And we can transition from viewing the Hubble image to one of the visualizations that our Adler team created specifically for these lectures to help take us on this journey together. So key to note is that this isn't an artist rendition. It's a visualization of the data outputted by the FIRE simulation. It's a model run on state-of-the-art supercomputers and built through an international collaboration, including Northwestern University researchers. The simulation follows millions of particles as they react, based on the laws of physics, to their surroundings. The fact that the visualization matches so well to the Hubble image is a testament to how well we understand the physics of galaxy formation and evolution. Granted, many open questions remain.
The red lines here that represent the winds flowing from the center of the galaxy, gas being expelled out into the broader universe. And that's believed to happen because of the number of supernovae that happen at the center of the galaxy. Now, our supernova didn't occur at the center, it was a little way off. But these supernovae have a profound effect on their surroundings, not only in the initial explosion, but in what happens afterwards. As we zoom in towards the location, we're going to stop time a little while after the supernova itself went off. And what you'll see is a shock wave of material, what astronomers call a supernova remnant, heading outwards into space. Now this is material traveling extremely fast. It's traveling about 100,000 kilometers per second, and when you're moving that fast, you shock and excite anything you come into contact with. And so this sort of strangely biological surface here is the result of the remnant supernova interacting with its surroundings. Later on, these things have a much more profound effect. Supernovae are donors of material to their surroundings from which the next generation of stars will form. Now, I said this was a Type 1a supernova. That's particularly important because we can use these to measure the expansion of the universe. But also, these are responsible for many of the familiar atoms that make up our world and us. So you may have heard the expression that we're all stardust, and that's true. The material that our bodies are made with have been through at least a couple of generations of previous stars. But supernovae like this one are particularly responsible for elements like iron. So about 80% of the iron in your blood came from a Type 1a supernova like this one in M82.
Maybe it's my romantic French roots, but thinking about how we're all stardust will never lose that sense of magic for me. Over the years, Zooniverse has supported a few different supernova hunting projects. The general model is to have volunteers look for differences in before and after images of galaxies, like the ones we saw earlier. They're looking for the telltale bright point of light indicating a supernova explosion. The Palomar Transient Factory Zooniverse project ran from 2010 to 2011. In that year, Zooniverse volunteers discovered 60 new supernovae, including several Type 1a, which are essential for measuring the size and age of our universe. Through that year of effort, the volunteers had generated the training data needed for a computer algorithm to efficiently process the rest of the Palomar images, including all the new images the telescope was taking. This just means that the computer had learned enough from all the images the humans had classified that it had the information it needed to accurately process the rest.
Or so we thought. It was because we were relying on automated algorithms that professional astronomers around the world at many different sites missed this supernova in M82, leaving it to be discovered by a bunch of undergraduate students, admittedly intelligent, clever, and initiative-taking students. What had happened was that the computers had learned that anything as bright as the M82 supernova, or anything in a nearby galaxy, was likely to be an artifact, and so it was rejected by our automated search. If we'd been not looking at the data, if Steve hadn't been there, we would have missed this supernova completely.
And the lesson we learned from this and many other experiences over the past decade of machine learning algorithms becoming more and more sophisticated is that it's essential that humans remain in the loop, with eyes on the data, so that we safeguard this space for serendipitous discoveries. These discoveries, these surprises, are often key to transforming and at times revolutionizing our understanding of a particular field of study. It's only through a combination of human effort, with our vast capacity to recognize the unusual and the unexpected and the weird, alongside the efficiency of machines to quickly process the known, that will best take advantage of and make sense of these ever-growing data sets.
We're building systems that do just that, and we're going to need to be good at it with your help. We're going to take you now to northern Chile, to the Atacama Desert, where you're now sitting inside what will be the dome of something called the Large Synoptic Survey Telescope, or LSST. LSST is a remarkable project. It's as big as the biggest telescopes in the world today, with an 8.4 meter mirror, but it's going to act as a survey telescope, scanning the whole sky every 3 nights. What that means is that every night astronomers will have about 30 terabytes of image data to play with. To put it another way, if you took your mobile phone and you subscribed to the stream of alerts that the telescope will send out every time it's noticed that something's changed, you're going to wake up every morning to 15 million text messages. And amongst those text messages, there will be supernovae, there will be asteroids moving, there will be Kuiper belt objects out near Pluto, there will be the flickering of many stars, the blinks caused by the occasional planet, and even nearby galaxies will flicker as material falls down into their black hole. This data set will create an overwhelming need for us to be able to find the unusual objects that are really worth paying attention to. And for that, we're going to need the best of human ingenuity and the machine's ability to crunch through extremely large volumes of data, working together.
To showcase just how much data LSST is going to collect, the following sequence shows really how we're going to be hit with a true tidal wave of data. So this visual steps through the years since 1880, showing the 64,000 supernovae we've discovered pre-LSST. So here we're just going to focus on seeing supernovae. And every time you see a point of green or blue light, that's a supernova going off in that year from that particular galaxy. Over time, you'll see some big swaths or stripes of data come online as a new survey or new telescope was built. So much of this is driven by the technology and our ability to capture these. Now we're going to step through just the past decade, the past 10 years of data, with 45,000 supernovae discovered in that time period.
So that means 2/3 of the supernovae that we've ever seen have come in the last 10 years, the result of a remarkable amount of ingenuity by astronomers. But we're still not satisfied. To understand stars and the cosmos, we need to do better.
And so next, for reference, we're just going to zoom in on the 424 supernovae discovered in 1 month, back in November 2018. 424 in just a month. That's pretty impressive. But finally, here's the number we're predicted to discover in the midst of LSST live on the sky in the month of November 2023. We expect to discover 66,000 new supernovae in just that 1 month. This is the same total number of all discovered to date.
Zooniverse volunteers will have the same access to LSST as the professional astronomers. And we hope that many of you will help us explore this new, transient, changing, slightly overwhelming universe. As we go back to where we started, out amongst the galaxies, I hope we've convinced you, first of all, that science is about asking simple questions. It's about sometimes about spotting objects, of asking questions like, what is this blob? And then coming up with ideas and thoughts and theories and testing those to try and understand the cosmos. We've taken you from here, amongst the galaxies classified by Galaxy Zoo volunteers in the last decades, down into the Milky Way to pay attention to particular stars with interesting planets or perhaps alien megastructures. And then we came back out to look at the transient universe. So the supernovae you can see are still going off, though I admit we've speeded up the rate very slightly. We've learned that there's still a place, even in this universe of big data, for human ingenuity and for the potential to be shocked and stunned by the beauty of what we find. We hope you'll join us in exploring this universe of surprises. Thank you very much.
Thank you.
Great, thanks very much. We do have a couple minutes for some questions, and we'll take questions here in Chicago and also from our remote venues. So if you're listening in from one of those remote venues, now is the time to submit your questions. But I shared at the top of the program that there are a few places tuning in right now, just to give you an idea of where people are listening and watching. We have some of our venues that are watching this in a dome, just like we are in Chicago, others that are viewing it on flat screens and with virtual reality headsets. So just examples, some of our partners that we're working with today, Lurie Children's Hospital right here in Chicago, Looking for Group, which is a gaming group in Pittsburgh, Science Center AHA in Tartu, Estonia. Hello to our friends there. The University of Plymouth in England. So
Nice to have some Devonians. If anyone in Plymouth is on the line and knows what the Torquay United score was, if you could pass that through, that would be great. Sorry, soccer.
No, well, my team just won the World Series a few days ago, so I'm missing that victory parade back in DC as well, so it's all good. The Hearst Planetarium at the Ella Sharp Museum in Jackson, Michigan, the Casper Planetarium in Wyoming, Parque Explora in Medellin, Colombia, where it's still the middle of the day, kind of like it is here in Chicago, so buenos dias. Traveling Telescopes, a group in Kenya, so where it's very late at night, so habari to our friends in Nairobi. And then also the Ghana Planetarium in Accra, Ghana. Thanks for joining us today. Well, as I said, we just have a couple minutes for some questions. If you have a question here in Chicago, we'll take one or two questions here. Please put your hand up, and I'll bring a microphone around if you have a question here. Yep. Wait for the mic, and I'll be right there.
Excuse me, for the alien megastructure star, what's the current theory is? We know if you think it's a gas ring, how come it didn't show up in the infrared data?
Yeah, so that's exactly the point. So the idea was that there was this gas ring, this debris disk that we visualized. But that was an idea. It was a guess as to what might be causing the dips. So we went and looked in the infrared and we didn't see anything. And so therefore we know there isn't a disk there. That idea we rejected, which is why we came up with the idea of comets, which turned out to be wrong as well, or we think that's wrong. Jason came up with his beautiful alien megastructure, which I see we're showing off again. Got to use it if you've got an alien megastructure, you've got to use it, right? We think we've ruled that out, and so now there are all sorts of ideas, but people are still arguing about what the solution to this mystery is. And so, if any of you have theories, I would genuinely love to hear them because we're slightly stumped right now. You have to explain both the rapid dips and the long, slow pause or long, slow fading, but we're still arguing about this thing.
So my question is, when it comes to galaxies and other stars that have anomalous behavior, do you think that any of that could just be just anomalies that perhaps we don't fully understand the science behind yet? We haven't discovered that part of science?
Great question.
Very much so. And for those who are joining remotely, because the question was asked by a young person, I think what's so exciting about astronomy is it's all so many open questions. It's part of the reason I was interested in it when I was young, because there's so much left to understand. As with each new telescope that comes online, it provides us data that we can then sort through and try to use to answer these questions. And so part of also as Zooniverse projects is every time planet hunters, every 6 weeks, there's a new set of data that's coming from the TESS telescope straight into our system. And the volunteers are among the first eyes to look at that data. And we know in each set there's going to be the unusual, the unexpected, the weird. And so it's everybody can jump in and try to find those. And then together, trying to understand what might be causing one thing versus another. And slowly just going through the tests and experiments and finding which ones stick.
It's a bit like being an archaeologist, right? If you're an archaeologist, you could dig carefully, you pull up an artifact, and then you have to explain it based on what else you found and what else you know. Like archaeologists, we can't do direct experiments. We can take what the cosmos gives us. And so where we see something unusual, radio astronomers recently discovered fast radio bursts, these pulses of light from the distant cosmos. We don't understand what they are, and so we're having a great time arguing about them. But you're absolutely right. If we've given the impression that we actually know the answers to all these mysteries, that wasn't the idea. We don't really know what's happening out there.
Well, I have two parts to my question. The first part is maybe I was wondering if you guys noticed any behavior very far away from the star. Maybe it could be energy from a quasar, from a supermassive black hole. Or maybe it could be something paradox-like, such as antimatter. I don't know.
Yeah, no, these are good questions. I think, so we have looked at the surroundings, and there's not much that's happening. In particular, we looked at nearby stars, and they're all normal. So we think it's a local effect. We think it's either something to do with the star, or actually something between us and the star. So some people have suggested there might be something passing much closer to us than the star, but it's relatively small scale. So I think that rules out the quasar. All sorts of exotic explanations are welcome. We're trying to get rid of the prosaic ones, and then if we can rule out a dust cloud and things like this, then we start to look at more exotic explanations. That's the fun of this game. So you might be right. I will come back in about 3 years, and I can update the odds on what we think is going on.
So we do have a few more questions about the universe and what we know about it, but more importantly, we have a sports update.
It's Torquay 4, Halifax 2.
Excellent,
final
that's
score.
really good news. Thank you. That's probably quite surreal for most of you, but I'll happily talk about that outside if you want to understand why that's important. Thank you.
So you can find planets by the dipping of light in front of the stars, but can you find anything on the planets that would indicate life, with current technology?
So there are definitely plans, and there's ways of looking at the light from a distant star, and even trying to, from the star itself, try to understand something about the planets around it. There's actually one of our programs here at the Adler Planetarium with our teens is high altitude ballooning, and taking images from 100,000 feet up in the air and looking back on Earth, and trying to use Earth, when you reduce it to just a pixel, to try to understand, well, what could we actually understand of a very distant planet around a distant star? Because it's so far away, the light from it might just be reduced to a pixel. It's this process of a detective work of trying to, because we understand our Earth very well, but when you reduce that information to so little, what can you tease out from it?
Yeah, what we've done so far is you look at the light when the planet's in front of the star, and then the light when the planet's out, and subtract one from the other, and you're left with the signature of the atmosphere of the planet. So if you can do that well enough, you can work out what's in the atmosphere. People have talked about looking, say, for oxygen. On Earth, oxygen is a sign of life. And so if you saw a planet that had an oxygen-rich atmosphere, you might be excited. Colleagues of mine in Oxford are working on a project called the European Extremely Large Telescope. It's the successor to the Very Large Telescope.
Again,
Don't let astronomers
we're not good
name
at
things.
naming.
Yeah, we were going to build something even bigger, which was called OWL, which was the Overwhelmingly Large Telescope, but that's still for the future. But the EELT will allow us to look around nearby stars and planets that are close to the star and do this sort of measurement for the first time. And then NASA is looking at a couple of possible missions that might launch in the 2030s that will have exactly this goal. Tell us what the atmospheres are like around the nearest 10 Earth-like planets. And at that point, I think that's really exciting. If you could point at a star in the sky, or yes, on the planetarium dome, and say, there is a star there that we know has an Earth-sized planet that appears to have oxygen in its atmosphere and is about the right temperature for our kind of life, I think that's a really exciting result, and it will happen in many of our lifetimes. So I think it's so exciting.
Chris, with the advent of computing power, it's becoming cheaper and cheaper to store data and process data. What will happen to citizen scientists?
Well, what we're finding is that there's a race. So we're finding that computers are becoming more powerful. Machine learning has had great advantages in the last couple of years, particularly at classifying things where you have a large set of training data. But you still need citizen scientists to spot the unusual, because it's hard to train a machine to do that. So what we're finding is that the digital revolution is increasing the capacity of machines to sort through the data, but it's also increasing the rate at which we obtain data. And so the proportion of stuff that you need to be seen by people drops, but the total amount of work seems to stay constant. And so far, we're betting that there will be a place for, say in the LSST era, we think only about 0.5% of that data will ever need to be inspected by a person, but it'll be the most important and interesting 0.5%. So the game is to let the computers do the stuff they're good at, and then focus this human ability to be distracted by the unusual where it's needed. And we're building systems, or rather, my PhD students are building systems, which do that, along with Laura's team here at the Adler, which allow us to do that dynamically. And so we're using the computing power to make better use of the time donated to us by the volunteers.
And we're going to finish with a couple questions from our remote venues.
Yeah, we have a data-related question from our friends in Ghana, Akwaaba, Ghana. They're wondering, who owns this data that's being collected, and where is it all hosted?
So for many of the astronomy projects, the data, whether it's NASA data that's being collected, that is owned by the public. So these are non-proprietary data sets. When you go online to Zooniverse, you're working alongside the researchers on data that your tax-paying money has helped make possible. So it is truly and it should be a true collaborative and owned effort. A few of the projects on the Zooniverse platform have been collected, in a sense, privately, but then there's always this agreement of how the data can be shared in what ways. So for example, the Gravity Spy project, it's searching for gravitational waves, or really helping the researchers make sense of the data that the LIGO detectors are obtaining and cleaning the noise out of that system. But because that data is, in a sense, owned by the LIGO collaboration, there's ways of removing certain amounts of metadata from those images so that the volunteers can be incredibly helpful and useful to the research teams, but also, in a sense, go alongside the rules that collaboration have put forth for those data.
The other part of the question was about where it's stored. With LSST, I think we'll see something very different. We're used to astronomers downloading their own data and storing it covetously on a hard drive. With LSST, we think that we will have the data actually just down in Champaign-Urbana. But anyone from an astronomer from anywhere in the world can log in and use the computers there. So you don't need your bandwidth to download 30 terabytes of data a night, and you really don't need to receive your 15 million text messages. We'll do the filtering for you. But we are thinking hard about how to make sure everyone in the world can make the best use of this data. It has to be a collaborative effort, because we need telescopes in Africa, in Australia, in Chile itself to follow up on the discoveries that LSST will make.
Excellent. We've got one final question from our friends in Plymouth. We talked a little bit earlier about the origin of the calcium in our bones and the iron in our blood and where that comes from. What's the approximate makeup? What percentage of our atoms come from a type 1a supernovae versus kilonova or another source?
Great question. I don't have a number, but it's relatively low, actually. Type 1a are rare, and they're particularly good at producing sort of calcium, iron, that sort of range of the periodic table. So we do have a bit of type 1a in us, but I picked the blood deliberately. That's the place where that's the most important stuff. The rest of us comes from other supernovae, from more exotic objects. If anyone's wearing a gold ring, for example, that probably comes from the collision of two neutron stars. If you haven't seen it, there's a great periodic table online which shows you where each element comes from. And it's quite sobering to look at it and realize quite how many different stellar catastrophes contributed to your presence here today.
And then also to think about the start of our universe, it was all hydrogen and helium. So it's really only those cycles of star formation, star death, new stars, new generation of stars being born, those planets being formed out of that, many generations of recycled materials. So I think we were talking earlier, this is the second, or
we're at least the third generation.
We're the third generation here on Earth of this particular material from stellar life and death. And I find it just, it's one of the aspects I really love about being an astronomer, is feeling that connection just all the way so many billions of years into the past.
It's reassuring on a Monday morning, I find, when it's grey and miserable and the inbox is bulging. It's nice to think that we are actually connected to the cosmos.
Yeah.
Great. Well, thanks. Well, we're about out of time here. Just a couple things. If you're here with us in Chicago, if you have a couple follow-up questions, you can join us in the room that'll be on your right out there for a few minutes. Also, if you're here in Chicago or coming, and we're just a few weeks away from opening our new exhibition here at the Adler Planetarium, Chicago's Night Sky. It's all about how the sky above connects us all as humans, and it always has, and connects us in our community here in Chicago. So please come back and visit that. But no matter where you are, be sure to check out zooniverse.org. You can take part in a lot of the projects that you've seen here. You can also do it at our touch table here physically, as Laura was pointing up on the dome. But just go to that platform, zooniverse.org, and you can take part in all these amazing scientific discoveries. So I'll just finish by, first of all, by thanking our partners at the Kavli Foundation, whose support made it possible for us to offer these series of 7 Fulldome lecture series. They are active, as are we, in connecting with people with the discoveries of science, so we want to thank them for that partnership. I want to thank our theaters and visualization team, a few of who are sitting back there that ran this. Yes. But most importantly, I want to thank our 2 speakers here, Laura Trouille and Lintott, for taking us on this journey through our surprising universe. Thanks, everybody. Take care.